Along with the development of wearable soft robots and artificial muscles, research on materials for soft robots is attracting a lot of attention. Soft robots, which can modify their structures according to the operating environment, are highly interoperable with humans. They can also act like living organisms without complicated calculations. Due to flexible and soft materials, however, soft robots have fundamental limitations: significantly weak actuation force and slow actuation speed. Accordingly, there is an increasing need for developing flexible materials for soft robots which enable strong actuation force and actuation speed.
Recently, materials for high-power density soft robots have been successfully developed. The research team, led by Professor Jeong-Yun of Seoul National University, succeeded in developing soft hydrogel actuators that are fast and powerful. This idea was based on the principle that plant cells generate immense power. For the first time in the field of soft robots, the team has proven that soft materials can break hard materials and expanded the usability of soft robots.
Unlike animal cells, plant cells are surrounded by rigid cell walls, so they can harness osmotic pressure as turgor pressure. Turgor pressure supports bodies without hard structures. It can also dig deep into the soil and also break solid rocks or concrete. The osmotic pressure of a plant cell is dozens of times stronger than a car's tire pressure. The hydrogel used in this paper, which is mostly made up of water, has a three-dimensional hydrophilic polymer network. Its actuation force is very weak, but its osmotic pressure can be very strong, just like that of plant cells. Our team wrapped the hydrogel with a selectively permeable membrane, so its high osmotic pressure can be converted into actuation force. Using turgor pressure, we have also improved the actuation force of the existing soft gel actuators. Furthermore, we applied an electric field to cause electroosmosis and accelerated water flow into the gel. This has greatly increased the actuation speed of the existing actuator with slow actuation. Based on these two strategies, our team has developed a high power density soft gel actuator, overcoming the limitation of the existing soft actuator.
The details of the system developed by the team is as follows. To realize a strong and fast hydrogel actuator, turgor pressure and electroosmosis were used. In an electrolyte solution, a polyelectrolyte hydrogel wrapped by a selectively permeable membrane gets immersed. When an electric field is applied to the solution, the ions start to migrate. Inside the hydrogel, free ions nearby the charged polymer chain drag water molecules, accelerating the swelling of the hydrogel inside the membrane. As the tough membrane restrains the swelling, the actuator generates a strong turgor pressure. Using a flexible and elastic hydrogel, the team proved it was possible to generate more than 100,000 times of power compared to the material weight without an external power supply. The team also demonstrated that only about 1 gram of hydrogel could break bricks within 5 minutes. The team showed that an underwater structure was constructed quickly using superior portability and non-powered high-power actuation. It succeeded in developing a new soft actuator and building a physical model to predict performance. This will help in the optimal design of soft machines. The hydrogel turgor actuator developed by the team is an actuator which can obtain a high mechanical power output using even a small amount of soft materials. The hydrogel turgor actuator presented by the team for the first time in this paper is a soft actuator. It can be used in various fields such as robotics, prosthesis, rehabilitation equipment, disaster rescue, and fruit picking. It can also be actuated without the hydrogel's mechanical and biological compatibility, as well as an external power supply. So it's highly likely that the hydrogel turgor actuator will be used for underwater city construction or futuristic robots. Due to its high usability, the actuator has a much higher market value than the existing soft actuator.
Generally, Hydrogel-based actuators have low speed. The inherently low elastic modulus of the polymer networks lead to weak actuation stress too. Actuation by the diffusion of a solvent such as water, which is caused by osmotic pressure difference, also contribute to the actuator's low speed. That's why they have not been commercialized yet. To secure usability and stability, continuous research is necessary, including the development of high power density soft actuators. The hydrogel actuator using turgor pressure, which was presented by us, will help to find the direction of research on soft actuators. We also think our actuator will be the founding technology that will lead to the commercialization of soft actuators.
Compared to the existing hydrogel soft actuators, the hydrogel turgor actuator can produce 1,000 to 100,000 stronger actuation force per volume. They can also generate 1,000 to 1,000,000 stronger force generation rates per hour. The hydrogel turgor actuator's power density is 2.33 kilowatt per cubic meter, 100,000 times that of the existing hydrogel soft actuators, which is 0.00001 kilowatts per cubic meter. In the case of hydraulic and pneumatic actuators and dielectric elastomer actuators, which are common soft actuators, high power supply of 10-watt pumps and several kilovolts of high voltage power supply are necessary. In contrast, the hydrogel turgor actuator can be actuated with less than 10 watts of a low power supply. They can be actuated even without an external power supply, even though the actuation speed becomes slower. According to the technology roadmap for South Korea's robotics industry released by the Ministry of Trade, Industry and Energy and the Korea Evaluation Institute of Industrial Technology, the global actuator market is worth $740 million. The market for artificial muscles and joints is worth $1.18 billion. The market is expected to grow by 12.4% on average. The development of high power density hydrogel turgor actuators will improve soft robots' usability and bring us closer to the commercialization of futuristic robots.
Our team has developed the hydrogel-based high power density soft actuator based on electroosmosis and turgor pressure. Even though we used very soft hydrogel, the actuation force was strong enough to break a solid rock. We believe that the hydrogel turgor actuator will present a new direction for futuristic soft robots because it can enhance mechanical power while keeping the intrinsic advantages of soft materials.
This technology was introduced in the renowned journal Science and recognized by the international community for introducing the hydrogel-based high-power density soft actuator. The actuator can be actuated with a low power supply or even without a power supply. Based on the structure of plant cells, this actuator can break bricks with a small amount of soft materials less than 1 gram. This remarkable result again seems to show the mystery of nature. Hopefully, this research will present a new breakthrough in the development of futuristic robots.